In this video, we're going to discuss the basics of operating systems scheduling for the CPU. We need to discuss certain definitions before we start discussing the different policies for scheduling. First, the goal of the operating system is to increase the utilization as much as is feasible. That is typically done through multi-programming, wherein we have multiple different programs that are ready to run in memory, typically from multiple users, but not necessarily. Each of those programs that is ready to run has some kind of CPU burst followed by an I/O burst. This constitutes a cycle. There is a distribution to how these CPU bursts go. Whenever one process happens to be waiting for its input or output to finish, it's possible for another program to run its CPU burst. Most CPU burst times are under 8 milliseconds. There is, however, a heavy tail, which can go all the way out to 40 milliseconds, which results from longer running batch type processes. But primarily, we are looking at interactive processes, which run with very small burst times, under 8 milliseconds. So this is a graphic for how the program might be split up into a CPU burst followed by an I/O burst. We could have some loads and stores and addition operations, but as soon as we stop to read from a file, we have to wait for I/O, and that is the start of an I/O burst for this program. After we come back from the I/O, we might do some more stores, we might increment, we might try to write to the file then, and that's going to result in a really short CPU burst followed by another longer I/O burst. When we come back from that, we might end up doing more loads, stores, and addition operations, but then if we go read from a file, we once again have to wait for an I/O burst. It's the CPU scheduler's job to select from among all of the processes in memory that are ready to execute, which one is going to run on the CPU next. The decisions typically are not made all of the time. There are fixed points in time when the CPU scheduler runs. Those times include when the process that is currently running gives up the CPU voluntarily. For instance, when it switches from the running state to the waiting state because it has made some kind of a service call. It is also possible that that process is going to terminate, in which case it is also going to give up the CPU. If the running process gives up the CPU because it has issued a trap, then we consider that to be a time when the CPU scheduler is going to run in a non-preemptive way. However, if the CPU scheduler is beginning to execute because what just happened was an interrupt, most likely what just happened is that the currently running process was kicked off the CPU and sent back to the ready state. And similarly, when it comes back from that interrupt, it's entirely likely that some other process was waiting on that input or output, and therefore that process is going to switch from waiting to the ready queue. And it is the CPU scheduler's job in that case to make a preemptive scheduling decision. When we go to analyze our scheduling criteria, we are going to pay attention to the utilization of the CPU because we want to keep that as busy as possible. We want to pay attention to throughput, which is the number of processes that complete their execution per time unit. This can be less than 1 if there are no processes that fully complete their execution per the time that we are using. And it could be higher than 1 if there are multiple processes that complete execution in quick succession. It's also necessary for us to talk about our metrics. So we care about turnaround time, which is the amount of time to execute a particular process from the time that it enters the ready queue to the moment that it terminates. We also care about waiting time, which is the time that the process has been waiting in the ready queue for the CPU burst. So that's the time that it spends in the ready queue entirely, from the point that it enters the ready queue to the point where it begins execution is only one component of that. If for whatever reason that process is kicked off of the CPU back to the ready queue, it is going to add more time to that waiting time. The response time is the amount of time it takes from when a request was submitted until the very first response is produced. So this is not output necessarily. This is more important specifically when we're working with interactive processes for time sharing environment where the user is expecting feedback from perhaps multiple processes in a short period of time. So we want to make sure that we are maximizing throughput and CPU utilization, minimizing the turnaround time, the waiting time, and the response time. Next, we're going to start talking about different policies for how we can decide to allocate our CPU.